welcome to numerical ship and offshore hydrodynamics. Today is the lecture 53. Today we are again going to discuss about the ship hydroelasticity. What we are going to do today is that we are going to discuss about the overall structure of the code, like starting from the hydrodynamics and how we get the structural deflections. We really do not discuss much detailed about the structure analysis. Remember that hydrodynamic solution, as I said in the last class, more or less similar to apart from the body boundary condition, more or less similar to that what we discussed before for the rigid body case. However, in case of a structural solution, we are using finite element method, we are using the Bing model. Like the details of this is just, it should be a separate course, but however, whatever is necessary for this solving this particular problem, we are going to discuss in the future class. But today we restrict ourselves to demonstrate the overall pattern of the code. Okay. Now, this is the keyword that you have to use to get this lecture. Now, let us start. Now, this is the equation, the boundary value problem that we discussed yesterday, our last class, that is the total potential should be split into 2 and all these things, all these boundary conditions over here apart from the body boundary condition. Remember, here you can see here we do not have the body boundary condition, and that is what we discussed in the last class, that is where there is a change. Now, in case of a rigid body, this, as I said, it is only depending on the time, the velocity, not depending on the space. However, in case of a flexible structure, it is depend on the space also. Okay. And this is the Green's function, I mean that source potential or integral equation that we are going to use to get the solution for the phi, right. Now, here remember that this 1.7 and in 1.8, this is only for the floating structure. Now, in case of a forward moving body, there should be another term should be with this, which is about the water line, that is absent here. So, it is just another one term, that is it. However, this is the main integral equation for the floating body. Let us discuss this whole exercise for this floating body problem only. Okay. And then you need to differentiate with respect to the normal. So, from 1.7 you get 1.8. Now, in 1.8 you have to solve for the sigma. Now, once you solve for the sigma, again you go back to this 1.7 and you can get the value for phi. So, this is the basic structure of the hydrodynamic code, and this is what we have discussed in fact in last couple of weeks. It is started from the frequency domain panel method, then we have strip theory, then we have time domain panel method, in everywhere. Now, we know this is how we obtain the value for the phi. Now, here in case of the flexible structure, once you get this value for phi, we have to get the pressure as well as the force. Now, this force here, this 1.110, this force is that we do not want, because this is the force acted on the body and it is applied only for the rigid body scenario, right. In rigid body, what is happening? Suppose you have the ship over here, and then you just discretize with number of panels, and then you find out the pressure at each panels, and then you integrate this, and then you can get the total force, and this total force applied at the CG. This is for the rigid body. However, in case of a flexible structure, what is happening, that this pressure, now this force actually I really do not want at the center. What we need? We need a pressure distribution or the force distribution in fact. So, what I do over here now, in case of a rigid body we have the panels, and now I am happy with the getting the force here at the CG, and then I solve the equation of motion, and then I can get the value for the displacement, velocity, whatever that you want. Now, here what you need to do is that I need the force, it is the force per unit length. So, F per unit length. So, that means I need the sectional force. Why? Because this sectional force, that is my input to my structural solver. Now, see, similarly the moment, I mean not moment here, in fact very specific, we have considering the all kind of modes here. So, explicitly we really do not want the moment equation here, is simply the force equation, and then the structural element, we solve the structural problem to get the generalize the velocity and then displacement, etcetera, etcetera. Anyway, so now the problem is how I can find out the sectional force, right. I know that how can I find out the total force, right. I have this expression, the pressure term over here. So, I integrate this pressure dot n, and then I integrate over the body. So, if I write it in discretized form, it should be F is equal to summation I is equal to 1 to n. So, number of panel. So, then each panel I am finding out what is the centroid, that the pressure at the centroid of the panel, and then I multiply by the normal at that particular panel, and then I multiply by the area of this particular panel. Once I do that, then if I add everything, I can get the total force, right. Okay. But now, in case of the structural, the flexible structure, I want that sectional force. Now, let us see that how could I get the sectional force. Now, the first step what I need to do is, suppose I have a panel, I mean there is a many way for doing it, but that is what actually we do here normally. Now, this is that z equal to 0 line, of course, just a little bit bigger, so that you can get it. Okay. And then now let us first, now what I do is, let us do the paneling first. So, I am doing the paneling. I am doing it for some arbitrary fashion, and now let us draw some sections. So, this is the section 1, let us take, and then let us say this is another sections, and then this is another sections. So, this is another sections, this is another sections, this is another sections, this is another sections, another one. Now, we have lot of sections. Now, what we have right now, after solving phi, after the solution of phi, what we have is the what is the force value at that particular panel. How? Here the force value is nothing but my pressure at this particular, let us say P I the pressure, and then N I the normal, and then d s I. Of course, we know that. So, what now we can do is, I know that what are the panel between this and this section. So, let us say this is section line number 1, this is section line number 2. Now, within the section line number 1 and within the section line number 2, what I get is, I can get that all the panel. So, this is my overall the force between these two sections, and then what I can do is I can average out this force and I can distribute half here and half here. So, this is the idea. Now, here you can see there is a catch. What is the catch? Catch is, that is why I made this type of panel. Now, this is, let us take this panel. I just make a little bit darker. So, let us say this is the panel, and then this is my the section line. Now, you can see that some of the panel, I mean section lines are here, left hand side, some part of the panels in the left hand side of the section. Let us take, let us say 1, 2, 3, 4, let us take S10. Some part of this panel is, some part is the left hand side of the section 10 and some part is the right hand side of the section 10. Then how can I take the contribution of this panel? Now, this could be fairly complicated if I do like this way. So, normally we remove this possibility from the beginning. What we do here, let us see, this is how actually one should do the paneling. Now, you see that if this is my geometric input and I have every right to do that as per my choice. So, this is some trick we are following. Now, here again first I am doing the section lines. So, now this paneling I do later, first I do the section line. Now, once I do the section line, I make the panel such a way that this panel either start from the section line or it finishes at the section line. So, if I do this, now you see this is my paneling. Now, if I do this, I can avoid all sort of confusion. Now, this is the section line and then all the panel are within the sections. So, now I am ready to average out everything, right. So, now you can see within, let us say S I and S I plus 1. Now, within this I have 1, 2, 3, 4, 5, 6, 7, 8. So, I have this 8 panels. So, I can do the contribution using. So, I just add this I is equal to 1 to 8, this all 8 panels with P I N I into DSI, and then I can get the total force at let us call this F I, and then I average out this velocity by dividing by the length, sectional length L, and then I make half at this node and another half at this node. Now, you see that is actually we have done here. Now, here it is very nicely again demonstrated to you. I have, this is the section lines, right. So, these all are my section lines now. Now, here this all this phi I is distributed at the centroid at the panel. So, the question is, if I have this centroid of the panel, it is more simplified thing, right. It is more simplified because you can see within two section lines you have only one single panel, right. Anyway, so if I have the value at centroid, how I can shift this value to here and here. So, there is no as such mathematical formula is available. You can do as per your realistic thinking or common sense mostly. So, what we did here, we use this formula. Now, what we did this, we take, as I said, I take the all the panel contribution between two sections, right. Now, let us take for the first section we have now in general what we have that we have between two section line there lot of panel is available, but here in case of one only one side. So, in case of the first panel we are using only these panels. Okay. Now, in case of a section 2 or again in case of nth panel I am using only this sort of these panels, only these two panels, that is what is written, and then we are averaging out and we are distributing. However, in intermediate panels, let us say for this particular section we are taking from here to here and then we are averaging out. Okay. So, you see that is what we have done. In case of a in general section I, in general section I, what we do is we take this range between I minus 1 to I plus 1 and then we are doing the averaging of this particular section. So, that is where we are doing here. And in case of a first panel, I get this only for this panel, but I do not have this other side of the panel. So, therefore, I take the total contribution, I average out and then I distributed half this side and I distributed half this side. So, this is how actually we are transferring my centroid, the force at the panel centroid to the sections. Okay. So, that is how we are going to write the sectional force. Okay. So, as I said that it is normally very frankly it is the pressure is continuously varying functions, right. So, therefore, this may be an approximation, but this is justified because I am assuming that variation of the pressure also not very radical. So, if it is not, then this formula or this formulation definitely is going to work. However, maybe for impact problem this might not work very nicely. Okay, so, this is about that how we are transferring the force or the pressure from the panel centroid to the section line. Now, once I do that, then I can do the structural solution. As I mentioned, again we are coming, I mean I am coming back in the future class, maybe next class, about the details of how we get this and how we write that finite element formulation for this particular problem. Today we are just going to discuss everything in overall fashion. So, this is my Euler beam equation, and in the right hand side what you are getting that f x t, this f x t actually your that dynamic force that you are getting, that sectional dynamic force that you are getting from your hydrodynamic code. There are many people who use, so they I mean here we can write that that only the dynamic force. And in this the stiffness matrix, here you can actually do the hydrostatic force. Or maybe some people, in fact we also we use this hydrostatic force, we do not import into this stiffness matrix. This you are doing this hydrodynamic plus hydrostatic force here as a external force. So, many people they use this hydrostatic force inside here, and but in our formulation we have done this in the right hand side. Okay. And now this is the boundary condition shear force and bending moment 0, because you are assuming this sheep as a free beam. So, therefore, shear force and bending moment should be 0 in the both end, right. Now, this is a very this what is said that popular and well known boundary conditions, this thing. So, it is not much discussion is required here. Anyway, but I missed one point here, when actually we are using this normal, Yeah, this normal is a generalized normal. Okay. Now, what is the expression for the generalized normal? Definitely we are going to discuss in the future classes. Okay. Right now, today is just I am going to discuss the overall pattern of the code. Okay. Fine. Now, this is how actually the discretization I do. It is my beam model, and then I just make that section lines, and then we can have the element, and then this each of element have 2 degrees of freedom, right. So, we have that it can one is the rotation, another is the translation. And now, this is how we can write the generalized mass matrix, stiffness matrix, and also the force matrix. Now, each detail, as I said, we are going to discuss in the next class, and then finally, you can write the global equation of motion, which is 1.17. And then once I write this, then we are using some Newmark beta technique to get the sectional velocity, sectional displacement, and the acceleration. Okay. Now, this also the Newmark beta again we are going to discuss in the coming classes. Today point is not how I obtain this. This is definitely it is much this methodology definitely we are going to discuss in the next classes all the details about what is delta, what is beta, what is Newmark beta method, etc., etc. We are going to discuss next class, but today objective is suppose I am getting this velocity, this displacement, this acceleration, I get it at the sections. So, now I am writing a beam. The point is after solving this equation 1.18 and 1.19 right now, just leave it like this. I am solving this, and then I am getting all this displacement, the velocity at the sections. However, in order to run the panel method code, I need all this in fact this normal velocity at the centroid at the panel. So, now the problem is actually the opposite. Now, first we understand that I need the force at the sections. However, I have the force at the centroid, panel centroid. Now, I have the opposite problem. I have the velocity and the displacement at the sections. Now, I need to transfer this to the panel centroid. Now, how we do that? So, now this is the problem as I said. Now, each panel I have to apply this boundary condition, right, Vxi. So, this velocity I must know at the panel centroid. However, I know this value actually at the sections. So, therefore, how do I shift this velocity from the sections to the panel centroid? Now, you see here again I would like to say that there is not much very fixed method to do that. Okay. I mean you can do many ways, like you can do in fact if you ask a random person like you can ask okay let us do it for a some curve fitting. So, curve fitting means suppose I have here the velocity I just try to figure out how the velocity distribution going over here. So, this section this point maybe this section it is this is the velocity. I mean what I try to say is that suppose I make a graph and then here is the velocity term and according the section along the sections what are the velocity. So, I have some point like this, let us take, and then I can fit a curve. It could be the quadratic curve, it can be some cubic curve. I mean, it become a curve fitting problem. Then see, you can do that, but there is, you cannot defend it physically. I mean, why you are using some kind of quadratic curve, why you are using some kind of cubic curve, it's more or less become a machine learning type problem. Like I have lot of data, I found out, then I can do this. However, if I try to approach from the fundamental understanding of the physics, I would like to think that this velocity or the displacement, I can assume that is varying also, almost like a straight line. There is no abrupt variation along the horizontal axis. If you do that, then that is what actually we are doing it. We are doing the linear interpolation. Okay, we have reason for that. Like if you look at that, if I get time, I will show you some results where you can see that when you plot the velocity or or other quantity along the length, then you can see that it is not very rapidly varying along the length. So, let us make it simple. Let us not make very complicated, like fit a cubic spline curve or fit a some nerves, something just fit a linear curve. So, that is what we have done in the, this is what actually is written over here, like an interpolation. I have these sections, I have another sections, I know what is the velocity over here, I know what is the velocity over here. Now, I have panel here, I know velocity here, I know the velocity here, I do the linear interpolation from here to here, and then I find out in this x location what would be the velocity. Okay, and this velocity again we fit into the body boundary condition, which is del phi del n is equal to, now it is V n x comma t minus del phi I by del n. So, in this equation again we put this, and again we are getting the phi at the next time steps, and again I get the force at the centroid. I change the force from centroid to the sections, and then I solve this structural problem using finite element, and then I get the generalized velocity and displacement at the nodes, I mean in the sections, and then I do the linear interpolation and change from sectional to the panel, and this is how actually we have coupled the structural FEM code with the boundary element code. Okay. So, today let us stop here. In next class we are going to discuss, because there is not much discussion left for the hydrodynamic solver. However, how I solve the structural problem, what is numeric beta method, how I use the finite element to get into this stiffness matrix or mass matrix, those we are going to discuss from the next class. Thank you.